So Russ Schumacher is a professor at Colorado State University, has a lot of expertise in mesoscale meteorology, mesoscale convective systems, heavy precipitation, flash floods. And Aaron Hill is a research scientist at Colorado State, and he has expertise in machine learning applications for extreme rainfall and severe weather. So this is a great tool. I'm sure many of you are familiar with this. It's a great tool to utilize to anticipate the potential for severe weather events or heavy precipitation events that can help you with your messaging. So thanks so much, Russ and Aaron, for joining us today, and I will turn it over to you.
Yeah, you bet. Do you see my slides as like slideshow mode?
They're not in slideshow mode.
All right, let me try to fix that. Let's do screen like that. There, that should be better. Yeah. Good. All right. So yeah, we're going to tag team the presentation here this morning. I'll start and then turn it over to Aaron after that. So yeah, it's great to be here and get a chance to talk about some of this work with everyone. You know, probably a lot of you are familiar with these tools already, but maybe some of you aren't. And we'll kind of step through what they are and strengths and weaknesses and how they work and all of that. So yeah, big thanks to our NOAA partners, Israel Iraq at Storm Prediction Center, and Mark Klein and Jim Nelson and others at Weather Prediction Center, and Ali Mazurek, grad student here at CSU, and Hannah McDaniel was our REU student last summer, and of course, big thanks to the JTTI program for supporting this over several years. So kind of the big question, you know, that we're trying to address with this work over the last several years is, can we use combination of reforecast data sets and observations and machine learning to get useful, you know, quote unquote, first guess guidance for the operational centers, looking at severe weather and excessive rainfall, and especially beyond day one, although we make day one products as well. So sort of, you know, tools that can be used in the forecast process in a you know, way that's beneficial to make forecasters' jobs easier or better or both. So if you're not familiar with the website, there's a QR code or there's the link. A couple of recent papers on the severe weather modeling system are listed here, and we'll kind of sprinkle some of the other ones in as we go as well. But you know, if you're not familiar with the output, it looks something like this. We'll show some examples as we go. So just to give some background on what we do here, I won't go into the real guts of the machine learning and all of that, but kind of give hopefully an overview that gives you a sense of how the system works. So the main kind of input data set we use for this is the reforecast data set based on the FV3 GEFs. So it's a 5-member ensemble that goes back, well, more than 20 years, but we use about 9 years of training data for the severe weather predictions. We use lots of different predictors. So, you know, environmental variables, ingredients type variables, so precipitation, capes-in, moisture, wind, shear, you know, et cetera. And then, you know, the training data set is the SPC severe weather data set for that same period. And so what we're doing right now is we make forecasts kind of like SPC, you know, analogous to SPC outlooks for the individual hazards, tornado, hail, and wind on days 1 through 3, and then the aggregate severe threat on days 3 through 8. And we also do excessive rainfall. Aaron will touch on that at the end. But these are the different regions. So we train models for 3 different regions for the severe weather system. And so we make these two runs a day for days 1 through 3, and then 1 run a day for days 3 through 8. And the guidance is going to SPC. They've been using it and evaluating it, and now using it in operations since mid 2021 or so. And so the machine learning method that we use is called random forests, and it's basically just a variant of decision trees. And so decision trees, that concept is probably fairly familiar. And so the way this works in the system is we might be trying to make a forecast at this red dot, and we might look at the information at this grid point and ask, you know, historically, if the temperature at this point was greater than 20 degrees Celsius, was there severe weather, yes or no? And then you might traverse down the tree with other variables, and you might ask the same thing for CAPE at this grid point, and all those other variables, and over the whole history of the data set, and you make random selections of these decision trees over all those grid points, all those variables, all those events in time, and see how they compare to what actually happened. And the end result is a probability of occurrence of that event. And so in our system, then, what, as I sort of mentioned, we would take all of those over time, every 3 hours in each forecast, all the variables, compare, find where the severe weather happened over all those days of training, and then that trains the model. And then for today, we would take today's GEFS output and run it through that model and get a probability of severe weather as the output. So that's kind of the quick overview, broad big picture overview of how the random forest works and what it's doing. So we'll now just kind of look at the performance of these forecasts over a couple of years of forecasts. And so we'll compare our CSU machine learning probabilities forecasts against gridded severe weather reports for about 2 years. And at spots, we'll compare it to the SPC outlooks to, just to kind of see how that comparison looks. And then when we do that direct comparison, we'll discretize our forecasts, which are continuous. There's no discrete categories, but obviously in the operational outlooks, there are the discrete categories, 5, 10, 15, et cetera. So we make it apples to apples as much as we can. Just for reference, the map on the right shows the frequency of severe weather occurring during that 2-year period. So it's quite active in the east and down into the southeast, not so active in the west. So that just gives you and that fits the climatology as well. So that just gives you a little context of where the events were occurring. So the first thing we might be interested in is how frequently do these machine learning guidance tools predict high probabilities of severe weather in relation to the operational outlooks. This is going to be something useful in operations. You don't want to be, wildly different. So this is for day 1 hail at the 15% threshold, just as a couple of things to look at. So this is the frequency of the SPC issuing a 15% hail contour over that period. On the right is the frequency of our machine learning system issuing a 15% probability for day 1 hail, and they match up quite closely over that period. So that's good to see. But as we go out to the longer lead times, for example, this is day 3 aggregate severe. You can see that the machine learning is issuing 15% outlooks a lot more frequently than the operational outlooks are. And there's a lot of different reasons you could come up with for why this is. Certainly the SPC tends to be somewhat more conservative at the longer lead times because you don't want to alert the public or the decision makers all the time on things that don't come to pass. But our machine learning system doesn't consider those sorts of things, and it tends to be a little bit more bullish at these longer lead times when the system is identifying ingredients that it thinks are warranted. And so I'll show a couple of examples to highlight that issue that we have. So the first example case is from the severe weather outbreak on the 15th and 16th of December in 2021. So this was the big, very unusual event through the Midwest, Nebraska up into Iowa and Minnesota. So here's the SPC day 3 outlook that was issued on the morning of the 13th of December. It's a less than 5% all areas outlook, which is probably what you'd almost always see in the middle of December in the Midwest. But our machine learning system had quite a different idea of what was going to happen on that day, and you can see this region of high probabilities through the much of the Midwest there, which is would be pretty unusual for mid-December. And so then if we look at what actually happened in this event, as I'm sure many of you are familiar with, this was a big severe weather event across the across that area. And here are the storm reports overlaid with the probabilities there, and you can see that the machine learning system did a really fantastic job highlighting the potential for a high-end event on this day. So this was a big win for our system. It's opening day tomorrow. We can have baseball gifts in here, right? So this is a home run. This is Andrew Lyons at SBC pointing out that the guidance played a role in upgrading. So they actually did kind of an unusual upgrade on the day 3 outlook, as a result of using our system. Unfortunately, not every day is quite that good. This is another example from just a couple weeks later where our system had some high probabilities in the day 3 outlook as well. And what happened in this case, basically nothing. So this was sort of a pretty big false alarm, swing and a miss type category for our system on this day. So this is the kind of stuff we're trying to figure out: is what are the cases where it's doing well, and why is it failing on the days where it's failing? So just to kind of look at aggregate statistics, this is Breyer skill score with respect to a varying daily climatology. So it's a pretty tough test for the forecast. Higher numbers are better. Machine learning system in green, and this SBC convective outlooks in purple. So on day 1, the SBC outlooks are better across the board. It's very tough to beat the expertise of experienced human forecasters on day 1, where you can synthesize all the observations and everything else. Day 2 for wind, the machine learning has a higher skill than SBC, and you get out to day 3, and you see that continues out there. So I think this is where we're seeing the value of the machine learning systems, especially out at the longer lead times where you don't have as much guidance available. And it can be really beneficial there. And then this is just another metric of forecast quality area under the ROC curve, and you kind of see a similar picture there, where and also where the ROC area on day 1 is pretty high, maybe suggesting that with better calibration of the forecast, we could improve the skill as well. Some of you may have seen these forecasts in the hazardous weather test bed as well. In both the 2021 and 22 HWT spring forecasting experiment, these were rated really highly by the participants. So just as an example, for tornadoes, it was the highest rated product generally in the 2022 experiment for tornadoes, except for NATOcast, which in 22 was rated higher. But still, you can see some of the comments here where the ratings were good. The ratings for hail were particularly good as well. And one thing that kind of jumps out to us in these comments as well is the mentioning of, despite using a coarse global ensemble as the input, which I think is showing that, as we all know, in the severe weather world, that there's a lot of information in those large scale environments. Obviously, the mesoscale is really important in the details, but the machine learning is picking out on the large scale environments and the key factors there. So, all right, I'm going to turn it over to Aaron now.
Thanks, Russ. So yeah, that's a good point to land on here too. There's a lot of information in the large scale environment, and in particular, how we can leverage that for longer range forecasts. Here's an example of some of our what we call medium range products, days 3 through 8, where day 3 is up on the top left and the 8-day lead time forecast is on the bottom right. And this was for the recent outbreak of tornadoes across Mississippi. And the main thing here as an example is kind of the ability to depict these areas of severe weather, even 7 to 8 days ahead of time. Maybe arguably the 8-day forecast is not particularly good, but there is some indication of an elevated threat of severe weather. And by day 7, the machine learning model forecast is highlighting that corridor really well. Perhaps maybe doesn't have probabilities in the correct area or at the correct magnitude, but there's some indication there that there potentially is a high impact weather event. You want to go to the next slide? So when we look at the skill kind of in the longer range in an aggregate sense, again, this is over that 2-year verification period, we can see both the relative skill against SPC, but also how it compares to climatology. So the kind of apples to apples comparison here is the light blue colors against the red. So those are using the 15 and 30% contours that SPC might issue for days 4 through 8. And you can see where the skill kind of starts to fall out is by about day 6, perhaps maybe not even eclipsing climatological skill, which is a Brier score of 0 there. However, and you might have noticed in that previous graphic too, where lower probabilities are issued tends to be where the system can derive a lot more skill. So if you include a 5% contour at these extended ranges, which is that darker blue contour, you can actually increase the skill of your system quite a bit. And relatedly also increases the area under the rock curve metric, which is a measure of discrimination. So where you see a 5% contour is really where the system is delineating that there will be severe weather in the extended ranges. Next slide. So regardless kind of skill and performance, one of the questions we have is, well, we have these forecasts that go out to day 8. Some of them do issue higher probabilities. To what extent does that actually correlate to high impact weather days? Can we say something about the system's ability to depict the general evolution of the atmosphere and how that relates to high impact days, regardless of whether that forecast is good or not? So here's 6 examples of over our verification period of instances where the day 7 forecast had a 30% contour in our system. So you can see for a number of these, the forecasts look pretty bad, maybe completely missed the areas and corridors of severe weather. Other examples where it's reasonable forecast. The number of severe weather reports is up in the top left of each panel. So you can kind of see for each of these days, there were a significant number of severe weather reports. But to what extent will that be useful to a forecaster? So you want to go to the next slide. One of the things we did is actually look at, for all of these day 7 forecasts, depending on what the highest probabilistic contour level was, what was the number of daily reports? So ideally, as your highest contour level increases, you want to see more daily reports. You want to see an indication that higher probabilistic forecasts are associated with larger, more high impact days. So on the left is the SPC forecast. That left panel is when no contour was issued. You can see the high variability. At day 7, SPC is going to be conservative. They're going to miss high impact weather days, but they're also going to hit some of them. Again, not really that surprising. But when they do issue 15% contours, there is kind of a change in that distribution in the box plot. You do see a shift of the medium up to about 100 daily reports. Now, SPC during our verification period never issued a 30% contour at day 7. But our system did. And so if you look on the right, that's the CSU MLP forecast. Again, the same kind of signal here. When no contour is issued, you did get a lot of variability. When a 15% contour is issued, that distribution starts to shift up. But when you get to 30%, you get an even more dramatic shift where you have almost a median of 200 daily reports. Again, indicating regardless of what the skill might be of that particular forecast, the mere presence of a 30% contour is highlighting a potential significant event. Next slide. So we've talked about severe weather, but we do want to kind of touch on the fact that we do this for precipitation, which is also a convection hazard. So one of the big problems we have with rainfall, though, is we don't have a great definition. And forecasters need probabilistic information about these rare events. And we have kind of clear definitions of what tornado, severe hail, and severe winds are, but we don't have that for excessive rainfall. We know tornadoes have to have some kind of damage indicator. Severe hail is greater than an inch. Severe winds are greater than 60 or 70 knots. I can't remember that exact threshold, but it's up there. But what do we do for excessive rainfall? Do we use flash flood guidance? Do we use flash flood reports? Those have some inherent biases depending on where they're coming throughout the country. Do we say that precipitation greater than a certain threshold should be used? What kind of threshold do you want? Should it just be purely a measure of the rainfall that fell? But 2 inches in Idaho is very different than 2 inches in Indiana. So that can be problematic as well. And also, what precipitation estimation data set do you use? All these kind of feed into this problem of how to define excessive rainfall, which you need to build these machine learning models. So what we've done, we've used 2 different data sets, one that's built on fixed frequencies, or if you're familiar with average occurrence intervals. And these actually better correspond to climatology and wet regions across the country. So you might expect once a year a 5-inch rainfall across Georgia or Florida, but in Idaho, that same once a year rainfall might be closer to 1 inch or 1.5 inches. So it kind of accounts for the climatologically wet regions across the country. And we use the climatology calibrated precipitation analysis data set, which is I guess a correction on the stage 4 using rain gauge observations. And specifically, we look at the 1 and 2 year ARI exceedance thresholds over these 24-hour daily periods. So that's we have a system built on that observational data set. And we also have a second system built on the Unified Flood Verification System developed by the Weather Prediction Center and Mike Erickson. This is what I like to call a hodgepodge of proxies of excessive rainfall. So they have flash flood reports, exceedances of flash flood guidance, or 5-year ARI thresholds, reports of flooding from the USGS stream gauges. They have just a bunch of different types of proxies for excessive rainfall, but it builds this really unique data set that maybe gets a little bit farther into the nuance of impacts rather than just rainfall. So next slide. Here's an example of, this is from the fixed frequency model. Again, just wanted to show an example of what these look like. This is from just a few months ago across Florida, not Florida, excuse me, California, when there was landfalling atmospheric rivers. Again, you can see an indication out to day 7, perhaps, where there might be excessive rainfall. And if we overlap the observations for that same day, you can see the skill of that system really kind of goes out that far, where there's some indication 7 days ahead of time that there's a threat for excessive rainfall. And the observations here are from the UFVS, and they're smack dab on top of the highest probabilities by days 3 through 5. So a really good forecast for our system. But as we alluded to in the severe model, we have bad forecasts too. You'll notice on this day, we have a highlighted, threat out to day 6 of maybe 28% or so, kind of a midway point between the slight and moderate threshold that WPC would put out in their excessive rainfall outlooks. And that probability actually wanes with time as you get closer to the events, which better corresponds to the fact that we only had just a handful of observations. You'll notice the points in Alabama and Georgia there. So not a really good forecast. And this is something that we really would like to learn a little bit more about. And one of the ways that we can do that is by kind of interrogating our models, which I'll talk about in just a little bit. Okay, so for these precip models, we're looking at the aggregate skill again across the kind of full range of our products from day 1 through day 8. The different colors here are their different versions, where purple is the fixed frequency model and the teal color is the UFVS model, again, over these 2 years of forecasts. Kind of analogous to the severe weather model, we do have skill out to about day 6, which is really fantastic. I don't think there's really much comparable that can drive skill out that far. And it's something that forecasters really have clung onto with these forecasts, is that there is value and there is information here that they can use with their experimental products, even out at days 4 and 5. And so one of the ways that we would like to improve the system going forward is maybe even to extend that and increase that forecast skill up to day 7 and 8 using some different types of techniques in the machine learning realm. So again, as I alluded to, we want to understand what these models are learning, how they're using the information. One of the ways we do that is something called variable importances or feature importances. This is a way of kind of more or less confirming that the models we're training across these different regions across the CONUS are learning something meteorologically relevant and something that we also understand. So the precip models are actually trained in subregions of the severe model. So you can see that up in the top right. Again, this is more or less driven by climatology, and where you would expect excessive rainfall across the Pacific coast maybe is more, is maybe different than what you would expect across the Great Plains. And so we kind of diagnose and train models in different regions because of these different unique environmental precursors for these events. So here in the bottom panels there are these feature importances, where higher means that variable is deemed more important or being used more by the random forests. So you can look at these different regions, for instance, Pacific Coast region, where some of these variables pop out a little bit more. Accumulated precipitation or the model-derived rain field ends up being the most important. But if you look across the Great Plains, Northern Great Plains or Southern Great Plains, you start to see precipitable water get more emphasis in the models. Again, highlighting maybe these convectively active regions are more dependent on the availability of moisture, but maybe areas that are driven by large-scale precipitation and large-scale dynamics are a little bit more focused on what the model is predicting. Again, these things are not necessarily surprising to us, but it's confirming that the models are learning something that we would expect and also builds confidence in the forecast products with forecasters. So towards the future, kind of some new products that we're developing in this realm of explainable models or explainable artificial intelligence is trying to understand how the models are using the real-time information about the environment and how that's being inputted into the actual forecast probabilities. So one of the methods we're using is tree interpreter, and a lot of this initial work was developed by our REU student last year, Hannah McDaniel, where we started to plot what these looked like relative to the forecast probabilities. So if you go to the next page, you can kind of see the evolution of what one of these variables, in this case it's CAPE, how that contributes to the 24-hour forecast probability, which are those solid contours. So you can see throughout the daily forecast period, the importance of CAPE changes, as you would expect, as the diurnal pattern changes. CAPE is highlighted more in the afternoon, but it also covers the almost full extent of that forecast area. And so we can start to plot and look at this information for forecasters. If you go to the next page, you can see these kind of panels of these tree interpreters, these contributions. So again, where it's blue is where the environmental variables are positively contributing to the forecast probabilities, and where it's brown is where it's negative, or like suppression of the probabilities. And we can start to say for particular forecasts, hey, this one's going to be driven by environmental buoyancy, or the forecast tomorrow is going to be driven by the kinematic fields, or it's going to be driven by maybe more mesoscale type features. And you can see instances of that in the precipitable water or mean sea level pressure field, kind of localized enhancements to the probability because of these variables. And so when it comes to issuing these forecasts and providing them to forecasters at these national centers, being able to say what is behind that forecast ends up being particularly valuable, and even maybe more so at the national or at the local level, at the National Weather Service offices, local levels, where maybe they can really dive deep into these forecasts and these contributions and understand a little bit more what's behind them. And last but not least, I do want to mention that the collaboration we've had with the national centers, with the NOAA test beds, has been probably the biggest highlight of this whole work, and understanding operational needs from forecasters, understanding how they would like to see these products displayed to them, etc., has been a huge aspect of this work, both in the flash flood and intense rainfall experiment and the spring forecast experiment as part of the hazardous weather test bed. And we recently just visited SBC and the Norman office to kind of talk to them about what they would like to see, improvements, how they would like to digest information about interpretability and these contributions. And hopefully moving forward, we'll really kind of develop this collaborative environment that we can propel into developing the models even further and really tailoring them to specific needs within NOAA. Okay, so a quick summary. You can just read this, but we've developed these systems that are pretty competitive with the operational outlooks, both for WPC and SBC, but especially beyond day one, where we think the real value lies in these systems. But there's a lot of opportunity for advancements, both in the forecasts and how they can be applied and understood. And this last point of how we can build trust with forecasters so that even in the midst of busted forecasts, we're not losing that trust. So again, our real-time forecasts are down there in the QR code. Happy to take questions now, or you can contact us via email as well. Thanks so much.
Great, thanks Russ, and thanks Aaron. Great material, great work, and just so useful for us in the field. So if you have questions for Russ or Aaron, please raise your hand or type in the questions pane. I have a couple. One of the things you mentioned, Russ, was that it could be improved with better calibration. How would you see that being achieved? How would you better calibrate it? What would you need, I guess?
Yeah, I mean, there's a couple different ways that could be done. I mean, one would be within the machine learning algorithms itself, with trying to adjust parameters and things, doing it that way. But now that we also have a couple of years worth of forecasts, then potentially we could sort of apply a second layer of post-processing to align the probabilities for with what is actually observed, and calibrate the probabilities better that way. And I think we see that especially. So the calibration kind of in the big picture is actually quite good for these systems, but we see the issues mostly in the hazards that are less frequent, like tornadoes and hail. And then also, I think the other aspect is in the spatial coverage. I mean, I'm sure folks at the WFOs have noticed too that the forecasts do tend to cover broader areas than what the SPC outlooks do, and sometimes that's warranted and sometimes it's not. So that's kind of another area. I know, Aaron, if you've got other thoughts on that, feel free to.
No, yeah, I think you pinpointed it. It's either in the calibrating the forecast probabilities to, like, let's say, practically perfect hindcasts of what actually was observed in a statistical way after the fact, or actually going into the machine learning model parameters itself and saying, well, we really want to adjust, say, the spatial extent of the forecast probabilities, or we want to adjust the magnitude of the probabilities. We can do that with some of the hyperparameters that are embedded in the machine learning model. It's kind of a good and bad situation here. You might be tailoring them to what's observed, but then you may make some forecasts worse. In the end, in an aggregate sense, it makes them better, but does that lose some of the value? I'm not sure yet. So there are methods to do that, and perhaps the aggregate skill kind of highlights that, as Russ alluded to. When you have good discrimination, you have good area under the rock curve, but poor Brier score, that's a pretty good indication that you're maybe not well calibrated, or not as calibrated as you could be. So that's really that indicator there.
Great, that's awesome. Thank you for that excellent response. Another area, again, if you have a question, please raise your hand or type in the questions pane or chat. Another area that I thought was really interesting, or aspect, was the use of the GEFs. And you talked about how the GEFs does a good job picking up the large scale signals. If the GEFs goes to a higher resolution, that's going to be beneficial, I would assume. Or if you get to too high of a resolution, does it introduce noise and that sort of thing? I'm curious if there's a sweet spot there, or would higher resolution just be better?
I mean, I think for this, the most important thing by far is having the reforecast data set over a long record, a long history with the consistent model. So yeah, if the resolution of the GEFs increases and a corresponding reforecast run is released, then I think that makes everything better across the board. Where the challenge for these types of algorithms comes in is when you upgrade the operational model, but then it's different from the reforecast that the machine learning was trained on. And we've seen it, it doesn't, you can still run it that way, and it performs pretty well. But I think to take full advantage of model upgrades, that's where then you also need the the corresponding upgrade to the reforecast. And I think that's a big reason why we've done a lot of work trying to in training models from convection allowing models, but on much shorter records, and we haven't been able to get the skill for the doing the machine learning on the cams that we have been able to for the GEFs. And I think the big reason is because the longer training period makes a big difference. We're still trying to sort that out, but that's been our, at least we haven't done it for severe as much, but for precip, nothing we've tried in training the machine learning on the cams has been able to compete with what we get out of the GEFs.
Gotcha. Yeah,
which is just sort of an interesting result in itself, I guess.
Yeah, and yeah, great point about needing to have the reforecast being the same resolution as the ensemble. Otherwise, you're kind of not comparing apples to apples at that point. I know we've seen that with tropospheric anomalies and that sort of thing when the reforecast or the climatology is different than the ensemble resolution. Mm-hmm. It's clear that the ensemble is going to go to higher resolution.
Yep.
The question is, will you get the higher resolution reforecast, because that's like really expensive to run, and I don't know if we're going to get those or not.
Yeah, I don't know. That's the big question, and that's and I think we're getting close to the point where, say, the HER has a long enough record that, well, and the student in my group has been trying to work with the HER to once you get 4 or 5 years worth of data, then maybe that's enough. But we don't exactly know that yet either.
Okay. Well, we're excited to see some more
research possibilities.
Yeah, well, we're excited to see more about the high-res stuff as you work on it. So thanks again, Russ and Aaron, so much for joining us today and sharing your work. We love this utilizing this tool, and really appreciate your insights and kind of your expertise on this. So thank you very much.
And we love hearing from the WFO folks in terms of how you're using it, what you notice for your area. So don't hesitate to reach out and say, whatever, hey, this event, it was great, or this event, it sucked because of this reason, or whatever. Let us know.
And I'll mention we're happy to talk with your office too if you want to set up a call. We've done that for a number of offices now, where it's just kind of a in-depth Q&A to kind of understand a little bit more and where that value lies for local offices. So that option's there if you want. Just reach out.
Excellent. Thanks again. Appreciate you coming on.